So last time we finished this slide, we talked about what is UTP, right? Unshielded twisted pair. And then we talked about CATs. So if you are going to buy today from Home Depot a Ethernet cable, what CAT will you buy? Six. CAT 6 is what is today available for very reasonable prices. CAT 7 is very expensive. CAT 5 is very cheap. Okay, so no, but this question depends upon how much you want to go. I would do CAT 6 because you see, right now we have 10 megabit, and then tomorrow we will have 100 megabit. We have 100 megabit, right? We have gigabit right now in our offices. We will have 10 gigabit and 100 gigabits and so on and so forth. So the wire will become old very fast, or out of date very fast. So today, if you are wiring a building, particularly I'm talking about wiring an office building, you would not wire anything less than CAT 6. Yeah, question?
I was just going to ask, so is the normal Ethernet cable we use Cat 5? Or?
Ethernet cable you use Cat 5? Yeah, so the Ethernet cable, for example, here's the Ethernet cable. I keep showing this one here somewhere. You never know what Cat it is.
You don't?
Only thing you show on the box. Once it comes out of the box, all bets are off. It might say on the wire itself, I don't know, but I really don't know a way of filling out the CAT after it comes out of the box. When I buy it, they tell me, what price it is and what category it is, and then that's it. Once it comes and then I open the box, that's it. It might say on the wire, because there is so much writing on the wire, I never read them, but there might be something. Okay, any other question? All right. So CAT 6 is the one which is today, and CAT 3 is your phone wire, and the CAT 5, 6, 7 are all the Ethernet wires. Other wires that are used for communications are coaxial cable. Now coaxial cable you have seen, if you have any dish network or any cable network, anything that they use thick cable, right? Black cable. Actually it doesn't have to be black, it could be white. So the thing is, that cable has only two wires, one central metal piece and then the sheath, which is wire mesh, right? That is called coaxial cable, and in between there is a lot of insulating material and all that. So this one is very well protected in the sense that this doesn't radiate like the Ethernet cable, and it has very high, let's say frequency capability, so you can send a lot of data. So if you really wanted to send very high speed thing, that's why we use it for video. Video requires a lot more capability than the other things. So it can go up to 500 megahertz, and it is used in cable TV. We don't really use it for data communication, because as the time goes by, we are able to do more and more bits right in the unshielded twisted pair UTP, so we don't need to worry about this kind of cable. Now the next method is optical communication, and I start this cartoon that we are not the first one. Human beings are not the first one to use the optical communication. It has been being used since the beginning of time by fireflies for a very useful purpose. Basically when you see fireflies, they are actually optically, their signals are not random. All right, they use something called pulse width modulation. The width of the pulse says something. All right, and so with that, let's go as to how do we do it now. So we discovered optical communication just few decades ago maybe, and the way we do it is that we use an optical fiber. An optical fiber is nothing but a mirror. It's a cylindrical mirror. So it's a cylinder. This is glass. This is glass. This middle thing is a glass, and there is another glass. So there are two types of glass. There is a core and there is a cladding. And the light, when it goes and it falls on the cladding, it reflects, and then it reflects again, and it reflects again, and it reflects again, and then it goes there. So that's how the light travels, by reflection inside a cylindrical mirror. But it is such a good quality glass that not much of the light is lost, and it can go many, many kilometers without too much loss. Like a normal mirror, if you take the one that we use every day, if you put 4 or 5 mirrors, the light is gone, right? But here, after millions of reflections, light continues. All right. So it is a cylindrical mirror. Actually, so there is a core, there is a cladding, and then there is something, there is jacket, which is simply this plastic thing, so that you don't basically get into the glass. But basically that's it. So there is a two types, core and the cladding. And the light is propagated by reflection, not affected by external interference. The good thing is that nothing can get into this. So if you send something, that is the only thing that gets out. There is no reflection, there is no antenna, there is no interference from outside. If you have a lathe machine going next to your wire or fiber, nothing happens. But if you have a lathe machine going next to your Ethernet, the TV picture flickers. Right? There is no interference. Fiber is used in all long haul or high speed communication. So whenever you want to go very long distance, we use fiber. For example, all international communication is by fiber. And so there is a fiber under the sea between the countries. And all long distance means even between the cities. So from St. Louis to Kansas City, we will be using fiber. Copper doesn't go very far. Okay, so after a few kilometers we start using fiber. And infrared light is used. So have you seen infrared light? Anybody has seen infrared light? Every day when you use a remote control which looks red is infrared. Right? Yesterday, in the last class we had talked about the spectrum. So infrared is just before the red. Right? So most of the optical communication uses that infrared spectrum. All right. So wireless. Now, if you remember that electromagnetic spectrum thing, you remember that wireless was somewhere in the middle, and that middle is 2 to 60 gigahertz. I think book says something like 2 to 10 or something, but I have changed it to 60 here because there is a lot of activity going on in 60 gigahertz right now. And so the book is actually 2006 or 7. It might have been written 2 or 3 years before that. In the last 5 years, 60 gigahertz has gone up. Like basically in lot in activity. So that's the right number. And so that could be terrestrial microwave or satellite microwave. So many of you have seen the satellite dishes on the top of the buildings. They are pointing to satellites, very long distance, I don't know how many thousand kilometers. They use microwave. By the way, anybody remembers what is a microwave? That was the spectrum that was shown earlier in the picture. This is microwave from 1 meter to 100 micrometer. 1 meter, 100 micrometer. That is microwave. So that spectrum, which goes from almost something less than a gig to 1 terahertz. That is most of the spectrum that we use in the wireless communication. And just like light, this is highly directional. So if you point your antenna this way, it goes there, just like the light. Actually what happens is, more higher spectrum, more you go in this direction, more directional it becomes. So this is light, and so the light cannot go behind a building. So if you have a sun, you go behind the building, there is no sun, right? But as you go away from here, lower frequencies, they are not straight lights. They can go behind, depending upon the building size and the frequency that you're using, and the wavelength actually. So these things can go behind, but they are mostly going in directional. So basically, you can point antennas, and in high-speed communication that we do in wireless. By the way, I teach a course on wireless, and that's my area of research as well. So if you use wireless communication, then if you want to get long distance or something, then you point your antennas into the right direction. Just like you can point a flashlight, you can point an antenna, and you will get a lot more signal with directional antennas than without directional antennas. And they can be made point to point as well as point to multi-point actually. So this is, I would change that to both. See, one thing about the wireless is that it is, while it is highly directional, you could make it non-directional and you could just light up the whole area in all directions. All right, then, so this is this is 2 gigahertz onwards. If you go down in the frequency, yeah, okay, so that's what they're trying to say in the book, is that if you go down in the frequency, then it becomes omnidirectional, and that becomes broadcast radio. So most of the television and radio that is transmitted today uses that frequency, below 1 gigahertz. In that band, it goes in all directions, and it goes actually much farther as well. And then very high frequency is light, and so this is not really used. I mean, like, okay, here's the thing though. I mean, like, we talked about optical communication, but that can be called wireless because there's no wire. But I would put that as optical communication separately. But anyway, if you use this frequency, then you're using infrared, and you cannot go very far, and that's why your remote control does not go very far. When you use a TV remote control, it is limited to few meters there, unless you use it in fiber, in which case it can go kilometers. But in the open air, it cannot go very far. Any question about that? All right, so much about the media. Now we are going to change the whole topic. So let's just summarize the media. So we talked about wires, shielded and unshielded. Unshielded, we talked about different categories. Then we talked about optical, fiber, and then we talked about wireless, right? And so these are the 3 kinds of media, right? Now we go into multiplexing. Regardless of what media you have, if you have one wire between 2 cities, many people are going to share that wire. Or what media? It doesn't have to be wire. Even wireless, many people are going to share that link. So how do they share? That is called multiplexing. So one way is to time share. So first the user 1 sends something, then user 2 sends something, then user 3 sends something, 4, 5, 6, 7, 8. This would be called time division multiplexing, TDM. Or we could frequency share. So I could use all the time, but I will keep myself in this frequency range, and second person could use that frequency range, third person could use that frequency range, and so on and so forth. That is called frequency division multiplexing. When you are doing cell phone, what are you doing? Time division or frequency division? Yeah, right. Actually, it turns out you do both, but initially when the cell phone started, there was frequency division multiplexing, and now today we do both, except that the time division is so fast that you really don't know that you are getting only 1 microsecond out of a minute, of a second. Because what they do is they take all your bits collected and then they send it in one burst. So you feel like you're getting all the time, because you're talking all the time, but the information is being sent in both combination of TDM and FDM. So each of these things is slotted in time as well. And that's how basically the capacity of the cell phone has gone up. In the beginning, when the cell phone came around, I remember 1980s, basically you could not have that many cell phones in a city, because it was frequency division multiplexing, and there were only so many people could, be given the frequency. But today we do both. So even one frequency is being used by many, many people at the same time. And then there's third thing which I haven't talked about here, because the book doesn't talk about here at this point, is space division multiplexing. Is that nowadays, if you are using the frequency at this time here, I could have somebody else use the same frequency at this time here, directional. Right, so space, so in a single city, the same frequency could be used at many places. So that's how we can put more and more people on wireless, or even on the wire, same for the same reason. So that is, so summary is there are two different ways of multiplexing, TDM and FDM. Now types of networks. This is historical again. I think I don't know, I have kept this slide, probably I should not, but anyway. So the thing is, the networks could be point to point, or they could be a bus, they could be a star. 20 or 30 years ago there was a big debate whether bus is better than the star, but today there is no debate. Basically there are two kinds of networks today, this or that. Point to point, when you go wide area networking, when you go from city to city, it is like this. It's just any basically point to point connection. But when you are wiring a building, it is always a star. So every port, if you have ports on a building, they all go to one closet. Single closet. That's a star. Yeah.
So why did star be out bus?
Outbreak bus, yeah. Because bus was very difficult to maintain and very difficult to find out where the problem is. With this one, you can just suppose you find out that the problem is somewhere, this guy is having a problem, you can just remove him and the rest of the people can work. And then you can work on the repairing. So it's much more easy to maintain. So in the beginning actually Ethernet was the one that was bus oriented, token ring was star oriented, but today Ethernet is star oriented. All the Ethernet wires go to the closet. Yeah. Point to point which are not wireless networks. You mean this one? This is wired. So I mean, this is any general network. You know, if you're going from city to city, they have laid down some fibers, and wherever there is a fiber, there is a link. Wherever there is no fiber, there is no link. So, yeah.
You can use like a crossover Cat5 to connect the computers together, right?
Okay, that's a different question. Let me set the question and then put a different answer to that. So his question is, can you use a crossover Cat5 to connect two computers? I would answer that question when we talk about Ethernet. Right now, I haven't talked about Ethernet. I haven't talked about what is a crossover. So it's too early to talk about. Yes, you can use crossover to connect two Ethernets. But, so that is your answer. But why that is and what that is, we'll tell you later on. Yeah.
So let's say these card strips that we have along here, actually you can plug an Ethernet. Wouldn't that be a bus though? Because we're all plugging in to...
Power strip? No. What you are plugging in is to a switch. And switch is exactly that. Old days we used to have a hub. That was more like a bus where everybody could listen to everybody. Today we have switches which basically you can't even listen to somebody. Suppose A is talking to B, C cannot listen to that because everything comes to the switch. Switch is smart enough to figure out which packet is going where and then only send there. So it's 100% that star.
It doesn't get sent to every Ethernet.
Yeah.
So are switches point to point?
Yes. So the question is, are the switch point to point? If you think about this link, it is point to point. These are all point to point links. But the topology is a star. You understand? So these are all point to point. So the link is point to point, but the topology of the network is a star or a bus. That's what we are talking about. Alright, so having done that, now let's talk about whether it is circuit switched or packet switched. So in the old days, when the telephone company was in charge, when you made a phone call, they reserved a wire for you. So they used to have switches in the phone company's switching center where when somebody made a call, they figured out that the call has to go through this switching center and then the switches will move and they connect the wire to some other wire. And that will connect to some other wires and you will have a completely physical wire connection between two people. Or there used to be an operator who would plug in and connect you. Yeah.
Just to be totally 100% clear, can you define what a switch is?
Yeah. So the question is, can you define what is switching? Now that's a technical question. I will give you two answers. One answer for today and one answer when we come to the discussion between switching and routing. Then it is much more technical. But today, whenever basically you want to send information from here to there, you go through some device and you go from port 1 and come out of port 2. That is what we're calling switching today. All right? So no, there is more complicated information because router does the same thing. You send the packets through one and comes out to the other, and we call it routing. But that is because I haven't defined what is routing and what is switching. So right now for today use when we say switching, and actually I was talking about the telecommunication circuit switching. Okay, hold on. Okay, all right. So one more time. So there are two things we can switch. So what the telephone company was, actually you came a little bit too earlier than what I was defining. So let me finish defining and maybe it will answer your question. So what telephone company was doing, they had a circuit and they used to connect the circuit to another circuit to another circuit to another circuit, and you have a whole circuit switched, and then when you spoke, every bit went along that wire, and they didn't need any packets, they didn't need any addresses, nothing. So that was circuit switching. Today the way we do information exchange or even phone call is that you have the information and as packets, and the packets have the addresses on them, right? Everybody has an address. You have an address, I have an address, and as the packets go, the routers look at this address and say, okay, it has to go that way, they send that packet this way, this packet has to go that way. So today it is what we call packet switching. Today what we call is packet switching. Previously it was circuit switching. In circuit switching, there are no packets. Understand? Yeah.
So circuit switching is basically you initiate the connection beforehand, right? And then during the communication, you cannot, no other users can intervene with that, right?
Yeah.
Whereas packets, it's like each individual packet is still identity. It doesn't really matter how many users there are. It's going to be forwarded to whatever user that packet belongs to.
Yes.
By circuit switching, it's actually the difference is like that the forwarding is done manually instead of automatically with the address.
No. There is no manual or automation issue here. Everything is automated today. There are circuit switching today also. So circuit switching can be automated. And packet switching is obviously automated. Okay? Let's see. So circuit switching means that basically, like, he explained that in circuit switching you have to set up the circuit before you can send the first bit. That takes some time. But once the circuit is set up, your bits go very fast and they go along the path that was set up, and so that is circuit switching. Packet switching is where you don't, you could set up a circuit, but basically you don't have to set up the circuit, you could just send the packet, so it goes very fast. I mean, it starts very fast, but then every place people have to look it up and worry about it. So packets are like this, and circuit is shown like that, where this is a blue circuit, this is a green circuit, this is a black circuit. So there are many circuits here, and the information is going in parallel, but the circuits have been set up. And this is packet switching, where this is a yellow packet, this is a blue packet, they're just different packets. Any question about that? Is that clear as to what is a packet? So packet basically is a set of bits. Let's say we generally use 512 bytes. So that many bits we take together, and then we put the address and everything else on the packet, in front of the packet, and then we give it to the router. Okay? And then the router sends it around. All right. Now, you still have a question about switching, or somewhat clearer? Okay. All right. So there is more technical discussion that we will have later on, but right now, for now at least, you know, the switching means moving the information around basically from one port to the next. All right. So the main difference is that circuit switching requires call setup. In packet switching, you don't have to have a call setup. So there is a way where you could, even in packet switching, you could tell that I really want to watch this movie for the next 3 hours, so please reserve this much capacity for me to the router. So, but that is not generally done. So you could have, this is optional. Overhead during the call is minimal because now there are no address bits, there is nothing else in this case in circuit switching, so there is no overhead during the call. In this case, every packet has an overhead. Stateful, what is a state? So in the circuit switching, the switches have to remember that this circuit is coming from A and going to B. If that switch died in the middle of this conversation, when the next switch comes up, it will not know what to do with this call coming from A. So that is called the state. That means there is some information that has to be remembered for this thing to function, and that state can be lost if the device that had the state is lost. On the other hand, in packet switching, if a packet is going from A to B, the router looks at the packet and says, I have to send it to B, and if that router dies, and then the new router comes in, then what happens? When they get a packet from A to B, do they have to remember anything? No. They just have to basically send the packet to B. So there is no state. And so the current internet actually is designed to be what we call stateless. So the routers don't remember anything. They can come up and down anytime they want. And believe it or not, that was the main reason why we invented switching, packet switching or computer networking or data networking, is because AT&T was the single point of failure. They were afraid in those days that Russia could invade USA anytime by putting a bomb on AT&T and be done with it. Right? Then we won't have any communication. But with the routers, they would not be able to do that, because with the router, they could kill one router, they could kill second router, they could kill 10 routers, but we could bring up 10 more right away and nothing happens. It's foolproof, it's fault tolerant. So that was the whole reason. Now it is used for very different reasons. But so packet switching has no state. Resource reservation is easy, but if you want something reserved, it is much easier to reserve on a circuit than on a packet basis, because that means remembering something which is difficult. Quality of service is same thing, is that basically you want to say, well, I want packets to be coming in 5 microseconds, so you want a delay guarantee, or I want 10 megabit to be given to me all the time, you want a throughput guarantee. That is called quality of service. That quality of service is very easy to do on circuit switching, very difficult to do on packet switching. Sharing is very easy on packet switching, slightly difficult on circuit switching. Now, I think that is also they are different from the book, because book says that you cannot do sharing, or it says something like that, but it is possible to share here. So, for example, overbooking is what is done in the phone company or in airlines also, is that if they have 100 wires or 100 wires capacity, they could give service to 200 people. Right? Because not everybody is using all the time everything. Right? So they could do overbooking. Same thing as the airlines do. When they have 100 seats on a plane, they sell 110 tickets, because 10 people will not show up, and they are fine, and they got 110 people's money. And so they always overbook. And yeah. I'm sorry, repeat it again. Can you say it loudly? My ears are not. Frequency division. Okay, let me see. All right. The question is, frequency, FDM and TDM, do they apply to circuit switching and to packet switching? The answer is, packet switching by design is actually time division multiplexing, but and so obviously FDM and TDM apply to circuit switching for sure. For packet switching also they apply, because when you do packet switching, and you have certain wavelength, say Wi-Fi, you're using Wi-Fi, then you decide how to send these packets. Who can send the packet? So you have a packet to send and you have a packet to send, then we could do time division multiplexing, or we could do frequency division multiplexing. So both of them apply to both. Hold on. So this is totally orthogonal in this. Does that answer your question? Okay, yeah.
So just kind of piggyback on that, why do you need overbooking if you have FTM and TDM and circuit switching?
Yeah. If you do a strict, if you hear a thing, overbooking is required because people do not use TDM. Suppose we have TDM, right? And I gave you a slot number 3, and you are going to use only, you don't speak all the time, by the way. When you are using phone conversation, you are using 50% of the time you are talking, right? Unless, something else happens. So 50% of the time you are listening, hopefully. And so 50% of the slots that are assigned to you for talking are going to go waste. So we could put 2 people on the same slot, right? Yeah. Okay. All right. So this is actually slightly different from the book. The book says that circuit switches requires dedicated resources and there is no sharing, but this is not true. Actually true only for CBR circuits. So there are circuits which are called constant bitrate circuit where you are guaranteed constant bitrate, but there are many variations of circuit switching, and so this is actually does not apply to if you don't have circuit switching. So that's why I have put that in blue, just to make sure that you don't get confused between what book says and what I'm saying. And the problem is that many of such statements we differ from the authors because first of all the world is evolving and the books are dated. Second thing is that people have different beliefs. Okay, some people believe in circuit switching and they will be pro circuit switching, and some people don't believe in circuit switching and they will just write everything that is negative. So in that sense, there is no common truth. There is no common belief that everybody says, yeah, this is right. Okay, so from that point of view, from my point of view, circuit switching can be shared, and circuit switching does not require dedicated resources. Okay, go ahead.
About sharing, I'm not sure maybe it's a definition, but should you underbook in order to share instead of overbook?
Okay, the question is, should you not underbook? The answer is, if you want strict guarantees, suppose you said I want guarantee 1 megabit and then I should be able to get it anytime I want 1 megabit. Then obviously I would give you 1 megabit. There's no reason for underbooking. I could just give you 1 megabit and 1 megabit to 10 people because I have 10 megabit. All right? So that is what we will do. But the usage is so bursty. So usage of your DSL circuit at home is 2%. That means that 98% of the time you are not using it. Right? It would be waste of so what happens is the phone company gives the same capacity to 50 people because 2% you are using, 2% they are using. It still comes out 100%, they get 50 times more money. At the same time, you are saving 50 times less money because you are paying 50 times less. Otherwise, they would charge you a lot. So if you want a guaranteed 1.5 megabit all the time, you pay a lot more than if you want 1.5 megabits shared. Where you get 1.5 megabit when you need it, but when you don't need it, somebody else can use it. So that is what overbooking is all about. Overbooking is about giving the resources to somebody else when you are not using it. It's the same thing in the airlines. They sell more tickets, and hopefully people will not show up. If some show up, then they give you extra money to get off. Right? And if they didn't sell that 10% extra ticket, everybody has to pay 10% more. Okay? All right. So now we go to a totally different, now this is actually much of an overview lecture, so it goes all over. So the next thing is what kind of networks we have. So there are 2 kinds of networks, enterprise and telecom. They are very different. Enterprise is WASU network. Any company, any university, they are all enterprises. Telecom is AT&T, Verizon, Sprint. They are telephone companies. They don't call them telephone anymore because they are not in the phone business. They don't make any money out of voice. They make more money out of data. When you have a cell phone, they make less money out of your phone than from the data plan, right? Data is where the money is. So they call themselves telecom companies. And so their networks are very different. They were actually much more different before, but they are becoming now similar. So they are adapting. So nowadays it is not very different, but still they are in the business of providing services to other people, whereas enterprises are in the business of using it for themselves. So the networks are different. So Ethernet is used actually mostly in enterprise. Frame relay is used mostly in telecom. So there are some protocols which are different. Now you don't know what frame relay, so it doesn't really matter. But the idea is that the telecom companies have some protocols that are not used in the enterprise, and the enterprise has some protocols that are not used in the telecom. Second difference would be the distance they go. So we have protocols that go only short distance. We call them local area network. And there are protocols that go long distance. We call them metropolitan area networks. And then some that go very long distance called wide area networks. Well, that was original definition of LAN, MAN, and WAN. Now they are all the same except that the ownership. LANs are owned by one organization. MANs are generally owned by the phone company and shared by many organizations, and WANs are owned by the phone company too. So they are more about the ownership than about the distance. Because Ethernet can go, previously 10 years ago when we used to teach the same course, we used to say Ethernet is a LAN technology. Today it is not. Today Ethernet is used even for MANs and for WANs. But that Ethernet which is used for WAN is owned by the phone company. The Ethernet that is used for LAN is owned by the organization, by the company owning it. For example, WashU or your own home, you have Ethernet, you own that Ethernet. But the Ethernet which comes from the phone company or which phone company uses is for everybody else. Yeah, go ahead.
Yeah, so earlier you said that long distances you use fiber.
Yeah.
But now you're saying that Ethernet you can use for long distances.
Okay, all right. The good question. So the question is, what is Ethernet? I keep showing you this cable. This cable is not Ethernet. That cable is simply a cable. On that cable, I can send anything I want. I can send Ethernet. Ethernet is a protocol. Right? I can send any kind of message on that cable. So we keep calling it Ethernet cable, but that is not really nothing to do with Ethernet. It's just a cable. I could be sending token ring protocol on that one. All right? So Ethernet can go on fiber. Ethernet can go on that cable, and Ethernet can go on some other cables as well. So that was the confusion you had. Is the question was, can Ethernet go on fiber? Yes. We haven't defined what Ethernet is. Ethernet is a protocol which we have not defined yet, but I have been calling that cable as Ethernet cable because that is what most of you are familiar with, right? I mean, when I say plug in your Ethernet, you just plug in that cable, and this so happens that nowadays we don't have any other kind of cables, any other kind of protocols. In our days, in old days, we had Ethernet, token ring, and different kinds of, many more variety. All of those have gone. All right, now the war has been settled in favor of Ethernet. So there is only one protocol. In fact, I mean, so that is the reason now. Anyway, so the idea is, Ethernet originally was, as I said, was the local area protocol, but now it is used everywhere. But they are different because of the ownership. The telecom networks, the telephone networks, are also of different kinds. Yeah, question.
Where do the enterprises get their internet from? I guess.
Where do the enterprise get their internet?
Yeah.
Okay. So the enterprise network is the network inside. So in WashU, they have lots of switches in the closets and lots of wireless transmission. These all belong to WashU. That is the enterprise network. But then they are connected to AT&T at some place, right? So that is where they get the internet from. Is that they are connected through the telecom company. Yeah.
Frame relay and also.
Yes. Question is, all the frame relay and ATM are also protocol? Yes, Ethernet is a protocol. So I gave an example here up to a protocol which is used in enterprise and a protocol which is used in telecom. And these are not really used in enterprise at all. We don't have frame relay in WashU. Alright, so let me go back to the last point. The telecom networks can be of three types: access, metro, and core. Access is the part of the telecom network that goes to the user, to the homes, to the offices. So the telephone company wire that goes, AT&T wire that goes from their switching office to your home, that is access network. The wire that goes between the switching offices is different, or may use different protocols. That could be one of the two types, either metro or core. Metro is the one that goes around the city, and the core is which goes between the cities, just like MAN, WAN, and LAN. Right? So the telecom networks are access networks, metro networks, and core networks. So one of the access technology, most popular access technology is, for example, if you go to AT&T and you say, I want 2 megabits, what kind of technology do you get? What is that service called? DSL. That's not Ethernet, by the way. DSL, that's a protocol too, right? So the idea is DSL is the access technology. That is not used in the metro or core. It's just used in the access. Yeah.
Just looking at electrical networks, they're more likely to use frame relay and ATM, but in metro and wide area networks, so they're all the same. They all can use Ethernet.
More and more. So the thing is, there are other technologies that they used to use before. Now they're adopting Ethernet for metro and wide area.
So instead of frame relay and ATM.
Yeah, instead of frame relay and ATM. Yeah. And tomorrow, I would not be surprised if you started getting pure Ethernet on the access as well. Right now I said DSL, right? Now the DSL today is actually, believe it or not, is ATM based. So when you get a DSL wire, you get ATM cells to your home, and then they put a device which converts that into Ethernet. Right? That's why you need that modem, DSL modem, which converts ATM cells to Ethernet packets. But Ethernet is not coming from the phone company. It is just starting from that modem. Yeah. ATM based. ATM is actually just like packets, but it's a different technology. Instead of packets, they use fixed size packets, and I think that should be sufficient for now, because there is. I mean, we are going to discuss ATM later on, more detail. But right now, all these terms are coming in because I have to use examples. We haven't even defined, for example, what is Ethernet, but we are using Ethernet because everybody knows. So ATM is actually a packet-based telecom thing where they use a 53-byte packet, fixed size packet, as opposed to a normal packet which are generally much larger and much more variable. All right. So the ATMs are like packets, but they are fixed size. All right. That brings us to homework number 1A, which would be due Monday. And so you need to answer 3 questions. Which network media will you use for the following applications and why? Very large file transfer at home, high-speed multiple channel video transmission at office, and news reading while traveling in a car. I think these are all very trivial questions, and probably you all know the answer, but you just write it down. Make sure that you read chapter 1 up to at least this far before answering these questions. Yeah.
So by networking media,
by networking media, I mean one of those 4 or 5 things we talked about here: STP, UTP, and coax, and optical fiber, and wireless. All right. So the next concept is, what is internet? So every company has a network. every organization has a network. When you connect many networks, that is called the inter-network. Okay? So inter-network is basically a network that connects many networks. And today, we don't know how many numbers, but this July 2008, they had 600 million hosts. I would not be surprised if it is now multiple billions of hosts in the internet. And a company that provides the service is called ISP, Internet Service Provider. Can you name an ISP? Yeah? AT&T. And so they provide access to the internet. And the telephone companies are examples of ISPs, AT&T, Verizon, Comcast. And Comcast is not a telephone company, but they are also ISPs now. They are the video service provider, right? And then the coffee shops. So most of the coffee shops provide internet access, so they are ISPs. All right. So the way internet works is that you have enterprise networks, then you have access, and then you have core. And these are also called stub networks. Stub networks, because they don't do any interneting among themselves, whereas these things are connected to many, many other places, and then they transfer packets. So these people's job is to transfer packets for others, whereas this one just does it for itself. So they are more like user, and these are more like the service providers. So this is a stub network. It's privately owned, not owned by ISP, and this is owned by ISPs. Access network is the one that goes from the users to the ISP, and then core is one which goes inside the ISP. ISPs are many different size. Big ISPs are called Tier 1. They provide services to Tier 2 ISPs. Tier 2 ISP provides services to Tier 3 ISPs. Tier 1s are like AT&T and Verizon. These are national providers, global providers. And then Tier 2 might be regional providers. So there are many companies which just rent facilities from AT&T. Or actually, even if they don't rent facilities from AT&T, they might use AT&T's circuits for going from one city to the next. So they are Tier 2, and then Tier 3 is local. Some people, they will just provide a small area service, and then they will use Tier 2 to handle the traffic going outside. So this is basically the size of the company: Tier 1, Tier 2, Tier 3, small, medium, and large. The enterprise networks use two technologies mostly, Ethernet and Wi-Fi. We used to have different things before, but nowadays those are the two. Most of you have just Ethernet and Wi-Fi, right? Ethernet uses the unshielded twisted pair. This one we have seen, and it runs as 10 megabits, 100 megabits, 1 gigabit, 10 gigabit. Has anybody got 10 gigabit? No. Does anybody have 1 gigabit? Yeah, almost all of you. The thing is, if you buy a laptop today, it will come with a 1 gigabit port. This laptop is new, it has 1 gigabit port. If you take an old laptop, it might have 100 megabit port. If you take an older laptop, it will have 10 megabit port. So as you can see, with every 5 years, we come up with a 1 factor of 10. Or with 2 to 4 years, we come up with a factor of 10. So the speeds are going up. So you would not be surprised if 4 years from now, you had 100 megabit, or 10 gigabits. Okay, they're working on that. So 10 gigabit is used right now today, but that is used mostly, inside the companies. So, for example, Vashu might have many 10 gigabit routers and switches, but you don't get to the desktop. It doesn't come all the way to the user because it's kind of expensive. But in few years, it will become cheap enough so that your desktop will have 10 gigabit. Originally bus, but now point to point. So this was the original Ethernet, but this is the today's Ethernet. Wi-Fi is called 802.11, IEEE standard, and it uses 2.4 gigahertz and 5.8 gigahertz. Those two frequencies. It runs at those two different frequencies, 2.4 and 5.8. And all of you have seen Wi-Fi, so I don't have to say too much. Access networks. In the access, the telephone company provides you access by many of these methods. Dial-up. If you have nothing else, you can just dial in, right? Many of you, I mean, at least I remember using dial in before. DSL is the next step. You can get a DSL service. Cable also you can get, or fiber to the home. So now I have fiber to the home. Actually, I don't think it is a fiber, but anyway, what I have is UVerse service, right? UVerse service is fiber to the curb, not fiber to the home. So the fiber comes to the neighborhood, and from there they just send it by copper. Fiber to the home is another possibility. Wi-Fi is another possibility for getting the access, and WiMAX is something that is coming in. So WiMAX is a new wireless technology which runs at much higher speed, but which goes for much longer distance. Actually, let me put it this way. So it goes 5 kilometers. Wi-Fi goes only 100 meters. If you put a Wi-Fi transmitter, you cannot get into the next building. In my home, I can't even get Wi-Fi outside of my home from inside. So it goes very limited distance. But WiMAX covers the whole city. All right. So that's coming up. So this cartoon is about a slow Ethernet connection. And Ethernet connection is always internet connection is always slow. So we have gone up actually in capacity. I remember getting 56 kilobit on. Now today we are at 18 megabits, which feels not very fast. In Japan and Korea, they are at 100 megabits. Okay, so they are ahead of us. I mean, we haven't heard of 100. Has anybody got 100 megabit? Home?
Well, I mean, no, but I was going to ask why we're so far behind.
Oh, why? You see, I mean, there is, but this is a long question, so I will not answer that question right now. Why we are far behind? This is a political question. But interesting part is that, and I wanted to share this story with you, that after having every country wanted to get ahead in technology, and right now the best way to get ahead in technology is to have the best communication technology, which is the internet. So every country spend a lot of money trying to get the latest technology first. And really, Korea and Japan do much more in this respect, followed by China and other countries. So Korea, Taiwan, and Japan, they are always ahead. So if you go into wireless, as you talk about wireless or anything else, they try to do it first. And government gets involved. So the government puts money into getting that done faster. Here, the government doesn't get involved. So that is one reason. It's only the companies can do whatever they want to do. There's no government incentive. So the idea is there. I also want to share this story because it's interesting. Is that in Korea, after 10 years of very high-speed internet, they found out that there's a big problem. And the problem is, what do you do with 100 megabit at home? Well, you can play much better games. You can play the games that you cannot play with 10 megabit. You can really, shoot very far and everything else. So they found that the students are not learning anything. They're staying home much longer, and they're staying at video games. And so now they're cutting down on speed. They're cutting down that basically, because too much of this is not very good, okay? All right. So dial-up. The way dial-up works is that you dial a computer, your computer has the digital bits, you connect it to a modem. Now I think for most of you this is history, but I just want to tell you because we went through this style. The modem will make the bits in a sound, in voice, and that will go over the wire to the phone company. All right, and then the phone company will convert that sound back into bits. So your modem will digitize it. Will convert the digital bits into some continuous sound waves, And because the access was all analog, only analog circuits can go there. So basically, and the phone company, inside the phone company, the core was all digital. So they would convert that back into bits, and then they will send it to wherever you want to go. And their end, they will do the same thing, is that they will convert back into voice and then bits. Yeah.
So today, even though we're not using dial-up, we still need modems, and that's just because of the switch from ATM to Ethernet?
Yeah. So right now the access is digital. Access is digital, so the bits can come from phone company to your home, but they're coming in the wrong form. Yeah.
Does that conversion limit the speed they can offer?
Well, not really. I mean, there's a little bit more overhead in ATM, and it is little more cost in ATM, and so that's why they will convert to Ethernet someday, but I don't think speed will change much. So anyway, in the phone company days, old days, when we had really the modems, the access was analog, so the only way you could get to the phone company is by voice, and so we needed a modem to convert your digital bits into voice. Everybody understand that now? Okay. So that's how it worked. A modem is modulator, demodulator that converts the electrical bits to sound waveforms, and then the telephone company were designed to carry only 4 kilohertz voice. That was another limitation. Basically, when the phone company wanted to design their wires, they had to decide what quality wire they should have, and they conducted a test. And they found out that if they can pass 4 kilohertz, then people are happy. Now, with 4 kilohertz, you would not really be able to send music. So nobody sends music over the telephone company's wire. I mean, really, it doesn't sound very good if you hear some song on the phone, right? So it was not designed for that. It was designed only for normal communication, right? For music, you need 20 kilohertz at least. But anyway, and so with 4 kilohertz, you could only do up to 56 kilobits. So that is where the modem stopped, and then we had to move on. So the question is, I have used the word Hertz bits, and I thought I will put something explanation as to what these are. The book doesn't have this, so please listen to this carefully. Bits are what we say, 0 and 1, binary bits, right? But to transmit a 0, how do you transmit a 0? To transmit a 0, there are many ways. You could do it that I will send plus 5 volt for 1 microsecond, and then I will send minus 5 volt for 1 microsecond, and that is a 0. And for 1, I will do minus 5 first and then plus 5 later. That is a 1. And that's actually a transition which is used, which what we call coding, that is used in many places. Okay, where a 0 is a transition down, a 1 is a transition up. So we just look at what is happening in the middle. If we see that the voltage is going up, that is a 1, the voltage is going down, it's a 0. Yeah.
How could you say 2 zeros at a time?
Yeah, you could send 2 zeros at a time. That's not a very difficult problem. You could just keep sending the same waveform again and again and again. I don't know, I have a pen here on this one. Yeah, you just keep sending. So you just send, this is 1 0, second 0. So you don't monitor this one. Okay, this is 1 bit. You monitor the middle of the bit. Does that answer your question? I'm coming to you. Who are here? Yeah. Does it?
How do you know not to get off of it?
Oh yeah, right. So there is singing in the beginning. In the beginning, we know exactly where the bit begins. So whenever any circuit comes up, like even your Ethernet, when you connect, there is something done to make sure that you know exactly where the bits begin.
Oh, okay.
Yeah. Okay. There was a question here. Okay. Yeah. Yours.
So how do you do like a 0 and 1?
Same thing. 0 and 1. See, thing is, send that first sequence and then send the second sequence. It doesn't matter what you send because in the middle we are just going to check. You could send 0, 1, 1, 0, 1, 1, 1, anything.
Can you draw these are ones just here?
Oh yeah. Oh, so you are basically you're confused about how do you come down from this, right? So what will happen is you are -1, and then you will be going like this, right? So this is your 1 and this is your 0, right? So you never went anywhere basically, you know, you could. All right. So this is 1 bit, this is 1 bit. Both of these are bits, right? However, when you send a signal like that on the wire, actually all these are going is sine waves, right? So this waveform might translate into some sine waves, which we do not want to get in here right now, but basically the frequency of that sine wave is what we call Hertz. How many cycles per second? So this one, for example, is if this was 1 second per bit, you will have 1 cycle per bit. Okay? And what about this half thing here? This one pulse, little pulse here. That is called a Baud. And so this will be 2 bauds per second. Smallest pulse that you have to send. Now let me tell you why we worry about the bits, baud and hertz. Because the sender cares only for the bits. The sender wants to send as many bits as they can send. Right? They want to send 2000 bits or 10 megabits or 10 gigabits. Sender only want to send bits. But the receiver cares only for the baud. Because the receiver has to be able to distinguish this little piece that it is up, and then in the little time it has to determine that it is down. So the receiver is limited in how many bars it can receive. Right? If I make that 1 nanosecond, receiver cannot receive. Receiver says, sorry, I just can't figure out in 1 nanosecond anything. Right? So the receiver has to worry about the smallest pulse that appears in the signal. Yeah.
I don't see why a Baud is not a bit.
Oh, okay. So it can be a bit. A baud could be a bit. For example, another coding could be that 0 is 0 volt and 1 is 5 volt. Right? Anytime you have a 0, 0, and this is 1. But that has its own problem, which I will not go into here right now. But so there are many reasons, a whole lecture on coding which we can give, but right now I'm not going to give that. But that's not coding. This is a coding. This is much more useful coding. Yeah.
So Wi-Fi is 2.5 gigahertz.
2.4 gigahertz.
2.4. Is it really nice? It's 2.4 gigahertz.
Actually, it's like now don't worry about wireless, because in wireless there is two kinds of okay, there are two problems. One is that 2.4 gigahertz is what we call the carrier, and then that is modulated with these things, and the modulation itself is only 56 megabit or 11 megabits or something like that. So we are talking about the modulation here. And this is what you brought up, is that this is translated into this right now waveform, and then this can be sent using another wave. So that's a whole physics which we don't want to get into, right? So yeah, so in Wi-Fi when we say 2.4 gigahertz, that is not 2.4 gigabits or anything like that. The bits are only few kilobits or few megabits, and so this is only few kilohertz, but then this is modulated on a carrier which is 2.4 gigahertz. Alright, so let me just repeat again, and this is important because it's not in the book but it's in the exam for sure. Bits are zeros and ones that you want to send, and the sender cares for it. Bauds are the smallest pulse size. There is another coding in which a zero is let's say 1/2 microsecond followed by 1.5 microsecond of low, okay, high and low. In this case, this is 1 bit, This is one baud, not that one. This is the smallest pulse that you have to send, the smallest time duration that the receiver has to worry about is the baud. So in this case it is 1.5 microsecond, this is half microsecond. And so half microsecond is what the user has to worry about. In some coding they take 2 bits and then they make 4 pulses. So this is 0, 0, this is 0, 1, this could be 1, 0, this could be 1, 1. Right? In this case, this is the baud, and if this is 1 second, you have 1 baud, right? But there are 2 bits per second. Does that make sense? I mean, so basically the number of bauds and bits could be more or less. Hold on. This has to be clear to everybody. That you could take multiple bits and represent them by 1 pulse. Yeah, go ahead.
So there's no such thing as a standard baud then, so it wouldn't really mean anything.
Well, a baud is unit like a meter. Yeah, so standard unit in the sense that you cannot say the baud is always 1 second. The thing is, baud means 1 pulse per second. Now here's another interesting thing is that when you say bits, we have to say bits per second. For hertz, we don't say hertz per second because hertz has a second built in. Right? When we say 15 hertz, that means 15 cycles per second. Right? Similarly, bauds, when we say baud, it is, when we say it is 15 baud, means 15 pulses per second. Okay, so I said many things. I just want to make sure everybody understood this. Yeah, go ahead.
Baud is a sequence of bits.
Okay, no. Baud is the basically inverse of the time of the smallest pulse. So if this pulse is half second, this is 2 bauds. If this pulse is 1/2 microsecond, then it is 500 kilobaud. Right? Half a million baud. If it is half a second, half microsecond is 2. Sorry, half microsecond is 2 million baud. Okay, so baud rate is inverse of the time of the smallest pulse in the coding. Alright, so the receiver cares only for the smallest pulse, and the pulse is measured in, you can measure it in seconds or you can measure it in baud. They are just opposite. Half millisecond is same as 2 kilobaud, half microsecond is same as 2 megabaud. Okay, alright, so receiver. And the wire cares only for the hertz. By the way, wire is designed for a particular hertz. So there are 3 people, sender, receiver and the wire. The wire is designed for a particular hertz, so you cannot, so it is fixed. So if the wire is designed for 4 kilohertz, you cannot, anything more than 4 kilohertz will be blocked by the wire. And so what will happen is, you have to design your coding such that if you want to send, you can send 8 kilobits through a 4 kilohertz wire. Alright, how? You have to design so that 2 bits require only 1 cycle. Right? Or 3 bits per cycle. And so this is a coding game, and there are people whose full-time job is to design coding, and they are working very hard because now we are able to send today. On the wireless, it is particularly important. Today in the wireless, we can send about 6 bits per hertz. We cannot send 7 or 8 or 9 or 10. Actually, some places we can, probably with a lot of money. So tomorrow they will discover how to send 7 or 8 or 10 bits per hertz. Then we will have even faster wireless. And that's how this WiMAX and Wi-Fi, etc. are working, is that they are discovering better codings so that number of cycles remain the same, but more bits can be sent. Yeah.
So the difference between Wi-Fi and WiMAX doesn't have anything to do with like signal strength or frequency.
So okay, so you're saying Wi-Fi and WiMAX has nothing to do with the signal strength? Yes, signal strength is the issue. So you can put more power and then you can go longer and things like that. But that there is a limitation there too. I mean, you cannot put too much power because otherwise people will get burnt. I mean, you don't want to stand next to an antenna which is transmitting microwaves, you will get cooked. That's what microwave is. Believe it or not, it's the same microwave, except that the microwave that you that you use in cooking is 700 watt or 700 kilowatt or something. It's not 700 kilowatt. It's 700 watt power, right? But the microwave tower that you stand next to is only milliwatt or microwatt. Okay, this antenna, this is transmitting right now. This is my laptop. This is an antenna, microwave antenna. It is transmitting few milliwatts. Okay, yeah, go ahead.
Yeah, I was wondering if you could give an example of where 1 hertz you could have 2 different encodings where one encoding would give you.
Okay, so actually we have it right on the board. This one is 2 bits per Baud, but cycle, let's see the cycle. Cycle could be very long, okay? And the worst case would be that somebody is transmitting 0, 0, and then this was 1, 0, 0, 0, 1, 0. So this is the smallest cycle you can get. And in this case, you can get 4 bits per cycle. This is one cycle. You can get 4 bits per cycle. So 4 bits per hertz.
That 0 always comes after 1.
Huh?
When you have 1, 0 down.
I'm sorry?
You have 1, 0.
No, I already just coding, and this was really randomly. I put a coding here where 0, 0 is this level, 1, 0, 1 is this level, 1, 0 is this level, and 1, 1 is this level. This is an example, right? In this example, you could have some cycles which are very long, and you can have 1, 2, 3, 4, 8 bits in that cycle. But in the worst case, you will have 4 bits per cycle. Right? So this will be called 4 bits per cycle, 4 bits per hertz. That example, you have 1 bit per cycle. This is one cycle. You start from 0, go up, go down to 0, and go down back to 0. This is one cycle. So this is 1 bit per cycle, 1 bit per hertz. This is 4 bits per hertz, and and so on and so forth. Yeah. Question? Yeah.
Is there is there work being done to get more, so we can have more levels?
Yeah. Everything is a cost. So when you have multi-level coding, then the receiver has to worry about distinguishing 2.5 volt and 5 volt, right? And then if you have 4 levels, then you have to worry about 1.25, 2.5, 3.75, and 5 volts. And remember, these levels, as the signal goes through the wire, after some distance, they become totally different. So the receiver has to do all that tough job. So it becomes more expensive. So the more levels you have, more difficult it becomes. Yeah.
The speed of transmitting 1 Baud is the same.
Speed of transmitting 1 Baud. Yeah, 1 Baud means 1 pulse per second. 2 Baud means 2 pulses per second. 100 Baud means 100 pulses per second. Alright, so you can have any number of Bauds, any number of bits, and any number of hertz. It is not necessary that for 4 kilobits you need 4 kilohertz. You could do 4 kilobits using how many hertz? 8 kilohertz, 20 kilohertz, or 1 kilohertz. Depends upon the coding. Similarly, the baud and the bit relationship. You could do any number of bits with any number of bauds, and so on and so forth. There are 3 different things and 3 different limitations. The receivers care for what? Baud. The senders care for what? Bits. And the wire cares for what? Hertz. And so if you want to get more hertz, you need a more better wire. If you need to have more bauds, you need a better receiver. If you need more bits, basically that's always good. So I mean, this basically I'm saying that the cost goes up when you increase any of these. All right. So here is an example, another example. This is a simple coding. 0 is a low and 1 is a high. This is called Y level coding. 0 is a plus 5 volt, Sorry, 0 is 0 volt, 1 is a plus 5 volt. This one will have how many bits per cycle? Yeah, 2 bits per cycle. And how many bars per bit? 1, yeah. Now here is another coding, which is the one actually I wrote on the board. This one is 0, 0 is the lowest level, 0, 1 is there, and 1, 0 is here, and 1, 1 is that level. Okay? So now, this cycle, as I said, is misleading little bit, because this is a possible cycle, but the worst case cycle would be the one that I wrote on the board here, where you could have just high and up, and all that. So this will have 4 bits per hertz, sorry, 4 bits per hertz, and then it will have 2 bits per baud. All right. Any question about bits, bauds, and hertz? Yeah, go ahead.
Doesn't that take longer though? I mean, if you want to get through all those stages as separate stages, whereas you just go up and down, it's the same shape, but it's closer together.
Longer means time-wise?
Like the cycle, yeah, I mean, this, so you said if you go up and down, like on the board, it's just only 4 bits.
Oh, okay. So this is what I was saying was that the signal, when we design these codings, we don't know what people will be sending. So we cannot just design so that people will be sending 0, 1, 1, 0, 1, 1, 1, 1, 0 like this, right? This sequence. So if somebody sends something else, the waveform will look different. And we want to design for the waveform that requires the maximum number of hertz. And this is the waveform, which is that somebody just sends the high level and then the low level and then the high level and the low level. If you do that, that would be like somebody sending 0, 0 and then 1, 1 maybe. And then 0, 0, 1, 1, 0, 0, 1, 1. That way you will have to cycle very fast. And that is, even that, it is 4 bits per cycle. 4 bits, yeah? Go ahead.
So cycles are constant time.
No. Okay. Question is cycle. What is a cycle? Cycle is going just one waveform, right? When you say a sine wave, cycle is going up and going down and going back to 0. So starting from a 0, going back to 0.
So what's the benefit of having fewer cycles?
So basically, so we are not talking about cycles, we are talking about hertz. Hertz is a cycle per second. So when we say 100 hertz, means 100 cycles per second. And some wire can carry that, some wire cannot be able to carry that many hertz. So when we say, let's say you have 500 hertz. So each cycle is how long? Seconds, right? 1 upon 500 seconds is 2 milliseconds. So cycle is not a second, cycle is different for that one, right? Okay, what's the question here in the middle? Yeah? Okay, so this one is 4 bits per cycle. Why is it 4 bits? Now that's a good question. Basically the reason is, given any coding, you try to draw a waveform that the user can send. So with this one, if the user sent this waveform, this is one cycle. One cycle is this long. Actually, let's start from here, and one cycle is this long, right? And how many bits are sent in that cycle? Red part, 1, 2, 3, 4, 5, 6, 7, 8, 16 bits were sent. So one could say, well, that's 16 bits per cycle, but that's a very good case. That's the best case. Somebody could just send 10, 11, 1011. In that case, you will be cycling basically they could be sending the lowest and the highest, lowest and the highest, lowest and the highest, lowest and the highest. Then in that case, each cycle will have 4 bits. Yeah. Go ahead.
We assume here that each 2 bits is in 1 second, per 1 second?
Each 2 bits is in one pulse. Now we could do any number of seconds. It could do in 1 microsecond, you could do it in 1 second. Depending upon what is the unit, you will have to have that many cycles per second.
I thought we defined the values, how many pulses to get 1 bit in 1 second.
Okay. Okay. We define baud as how many bits in 1 second. We define baud as how many pulses in 1 second. How many pulses, not bits. How many pulses? So here, each of this is a pulse. If this was 2 microsecond, how many bars is that? Yeah. Okay, let's make it easier. Each pulse was 2 seconds. How many bars is that? Half baud. Because each pulse is 2 seconds. So how many pulses per second? Half a pulse per second. If each pulse is 2 seconds, we have half pulse per second. Right? Is that a question for everybody, or is it? No. Okay. All right. Any other question left? Yeah.
Back to the question.
Yeah.
If the red is 1 second,
Yeah.
isn't that 6
Okay. Again, one more time. This time is over. Sorry, time is over. So we'll talk about